There is a Maclaurin series for natural log of 1 plus x that's given, and you can tell it's Maclaurin because it's centered at 0. And it converges on whatever its interval convergence is. And there's another function, which is x times the natural log of 1 plus x over 3. Okay, so we want the first 4 non-zero terms and the general term from the Maclaurin series for f. So we're trying to create a series for this. So the idea here is that we do not want to take the derivatives. I want to work off of this. So the only difference between this and this is, notice, instead of x, you need to replace the x with x over 3. And then notice, then you're going to multiply everything through by x. So really, x ln of 1 plus x over 3 is the same as taking the original function that they gave us here, replacing that x with x over 3. So I'm going to replace everything that they're giving us for x with x over 3. So, oops, yeah, this I just left as x over 3. X over 3 minus x over 3 to the 4th over 4. And then we also need to multiply everything through by x. And we've got the general term also, so I'm going to do that also. Okay, now I do want to multiply that x through, so we want to so it's written as terms. So my first term is x squared over 3. Now, you do not have to simplify anything, so I'm going to leave it just like this for right now. The next one is multiply that x through. There's my first 4 terms, and your general term will just have the x over 3, and then you have a plus dot, dot, dot. So there's part A. Okay, part B is now saying find the interval of convergence for this particular series. So in order to find the interval of convergence, we just need the general term, which we figured out here. So now this may be where you can clean things up a little bit if you want to. You don't have to. So I'm just going to do the ratio test on here because it's not a geometric. So wherever there's an n, I'm going to put an n plus 1. So this becomes n plus 2. I still have this. This is n plus 1. This is n plus 1. Multiply by the reciprocal, so let's flip it. And you will notice a lot of things will simplify nicely. First of all, notice that this is going to become unimportant because you're going to take the absolute value of it. These x's will divide out, and notice that the x over 3 to the n will divide out, so you're really left with just an x over 3 on the top, just to the first, and you have that n over n plus 1. Now when you take that limit, the ratio of the lead coefficients on the n is 1 over 1, so all you're left with is x over 3. That's my limit, so the limit statement should be gone. And we know for a ratio test, it only converges when it's less than 1. And I can solve this pretty easily, so I get to here. Now, this is asking for the interval of convergence. If it asks for the radius, you would tell them that the radius of convergence is 3 and be done. But this is asking for the interval, so this is where we have to go ahead and check the endpoints. Okay, the way that we check our endpoints is we're going to check each one individually. Okay, I'm going to go ahead and let's erase what I've got here and do my endpoint analysis here. So I need to check -3 and 3. Okay, so what we're going to do is take each endpoint and plug it back into the original sigma. So let's start with x equals 3. So I'm plugging it into here. So if I plug in x equals -3, I have this, I have a 3. 3 divided by 3 is just 1, right? And let's clean this. Oops, I don't have a plus 1. This is just n. And 1 to the n is always 1, so I don't need to write that. So I have this. Okay, notice this is an alternating series test, and if you check your condition, it is true that the absolute value of numbers go to 0. So you would say converges by the alternating series test because the absolute value of the numbers approach 0 or decrease to 0. Okay, so at x equals 3, it's going to converge. What about at -3? So do the same thing. We're going to plug it in here. So I have that -1 to the n plus 1. I still have a I have a negative 3 here. A negative 3 over a negative 3 will be a negative 1 to the n. I have this. And let's clean this up a little bit. If I clean this up, notice that you will end up with this has the same base, so I can go ahead and combine those exponents. So I have this. And notice here, as you plug in different numbers for n, this is always negative, but you always have a multiply by negative 3, so the top is always going to be positive. So really, this is the same as this series here. I should have a sigma here. So this is a p-series that diverges. So your interval of convergence here is really going to not include negative 3, but include 3. So this is your interval of convergence. Okay, last piece is asking about an error. So let's see what they're telling us. So it tells us that, oops, this should be part C here. There's a 4th degree polynomial for f about x equals 0. So really your 4th degree would be this, right? This is really your 4th degree here because you have x times x cubed. So there's your 4th degree polynomial. Use the alternating series error bound to find an upper bound for this error. So they're asking you to use the alternating series error bound and find that upper error bound. So what's the biggest error this could take on if you only used a 4th degree? So remember we learned that for an alternating series, your error just comes from the next term that you do not use. So in this case, oops, I erased this, there's a 4 here, that would be this term, right? We're only using these. So your error is going to be from this term right here. Okay, and what value of x are we trying to figure out when x is 2? So I'm going to plug in 2 here. So this is my error, and that's it. If you want to punch it out, you can, or you can just leave it like this. If you do simplify it, I believe it's 8 over 81.